Yeah.
Good morning, everyone. It's my great pleasure to introduce the speaker today. We're very happy to have Hannah Hsuan from the Chinese University of Hong Kong. He's going to talk about the whole Strominger system and geometric flows. Let's welcome the speaker.
Yeah. Before I begin, I'd like to thank Pak Yung for inviting me. It's very nice to be able to come here. Meet people and talk about math. So I'll be talking about Hall Strominger systems and geometric flows. This is sort of based on things that I did near the end of my PhD with my supervisors Sebastian Picard at UBC, and then also a bit more recent things done with Spiro, Carrington, at Waterloo. So a very brief outline for the talk. I will give a very quick motivation to the things that we're considering, and then we're going to look at two specific cases. So the dimension of the manifold that we care about, we'll look at it when it's 6, and these will be related to SU3 structures, and then when it's 7, it will be related to G2 structures. I'll give an explanation for these as we get there. Also, feel free to interrupt and ask questions if you have any. That's fine with me. All right. The very quick motivation is that the models that we're going to consider come from 10-dimensional heteronic string theory. I don't know anything about string theory, but this is just where the models are coming from. I'm not going to pretend to be an expert in the physics aspect of it, but what we mostly care about is models that the physicists use. So when they compactify their theory, they consider these models. So the product manifold has two pieces. It has the k-dimensional piece and the n minus k-dimensional piece. N is a Lorentzian manifold, and then the thing that we actually care about will be X. So it's Riemannian spin manifold, and it satisfies some additional conditions, and what we are going to investigate is the sort of conditions that need to be satisfied for their model. Okay. And like I said earlier, we'll look at what happens when k equals 6 and k equals 7. That will correspond to n being 4 and 3-dimensional. So when k equals 6, that's the most familiar setting, right? N is Lorentzian space, so there's 3 space dimensions and 1 time direction, right? So in their models, N is usually Minkowski space, but sometimes empty de Sitter space, which I know very little about, but I'll just mention those.
Meaning that if it is dimension k equals 7, capital N is dimension, you have to do a natural situation.
I don't know about natural in terms of modeling reality according to string theory. But it is another setting that you can cast an equation with.
I see.
Okay. So we're looking at conditions on X, and these are going to involve certain structures that we can endow into X. So they'll involve Riemannian metric spinners. It'll be this function called the dilaton, this differential 3-form, which is called the flux, and then we'll have some connections on these full buckets. And then, like I said, we'll look at what happens in the k equals 6 case and k equals 7 case. Alright, that's the very quick motivation. What we really care about are the models, so we'll very quickly dive in. When k equals 6, this has been a thing that's been studied for quite a while. Like I said, it's the one that seems the most familiar for studying reality as the string theorists back then. So in the 80s, Candelas, Horowitz, Strominger, and Witten looked at this flux-free case. So I said that these involve some differential 3-form. Here they've taken the simple case and set that 3-form H to be 0. And what they figured out is that in the setting when you turn off the field H, then our manifold X needs to be Calabi-Yau 3-fold, which we should like in a metric.
You just assume X is a spin.
Yeah.
There's a spin 6-dimensional manifold. In that case, it must be Calabi-Yau.
Yeah.
Why the H is here?
Not that I don't just assume that X is spin. There are other conditions with the field, and after you, they have this action that they're trying to minimize.
I see.
When you do the variations of that, the equations come out. Yeah. The equations come out, and then it ends up being this. So if you assume that the 3-form is 0, then it turns out that everything that comes out implies that the manifold needs to be Calabi-Yau. Okay. And so they can relax the flux-free condition and turn this field on. So in this case, independent work by Hull and Strominger showed that the 6 manifold needs to be still Calabi-Yau, but it has to be non-Kähler with constraints. And at this point, I will just make a remark on what I mean by Calabi-Yau. Yeah, you can see that I have Ricci flat Kähler, Calabi-Yau, and non-Kähler. When I say Calabi-Yau, I just mean complex three-dimensional with trivial, canonical bundle, and finite fundamental. So there's no requirement for it to emit any Kähler metric. Emitting a Kähler metric is a separate condition from being Calabi-Yau. Right. So what we're interested in are the constraints that Hall and Strominger came up with, and so this is the system. We'll look at what we need. So we need the base manifold, that will be X, and because of our definition of Calabi-Yau, it has trivial canonical bundle, so it has a nowhere vanishing holomorphic 3-0 form. I'll call this epsilon. So what does the Hall-Strominger actually want? It wants two metrics, but to define one of these metrics, we also need the additional vector bundle E. Okay? So we need to define a vector bundle E. It can be anything a priori.
There's a degree of freedom.
There's a degree of freedom, but usually when people solve the system, they take the E to be the tangent bundle, the holomorphic tangent bundle, because it's one of the more natural bundles to take up. In terms of freedom as well, there's the whole thing of conical transition, which is a process to deform these 6 manifolds, and ideally the solutions to this system works well with this transition that involves a degeneration, that involves a blowdown, and then you can resolve the singularities. And so just to make sure that the bundle exists on both sides of this process, people consider the tangent bundle, because every manifold has a tangent bundle, but if you take any arbitrary bundle, it's not guaranteed that it exists on both sides of this transition, right? So there's something like this. There's a cone over S2 cross S3. You can resolve the S3, or you can resolve the S2 or resolve the S3. So there's this. Yeah. So the process of conical transition, you can go from some manifold. Yeah. And if you do this conical transition, it's not guaranteed that the bundle you start with here exists on this bundle on the side of the transition. So tangent bundle is the more natural thing to take on. Although you're free to define it on any vector bundle. Okay. Anyway, after we choose our holomorphic vector bundle, we want two metrics. We want a Hermitian metric on the base, and we want a Hermitian metric on the bundle that satisfy these compatibility constraints. Okay. We also need to choose some constant alpha prime. Okay. I'll leave the equations there, and I'll define everything that shows up. So we have some curvatures appearing in equations 2.1 and 2.2. These curvatures will take specifically to be the Chern curvatures of our metrics. But in general, when you're considering the system, there's a freedom to choose any unitary connection. Something about this condition over here doesn't see the choice of metric, right? Doesn't see the choice of connection, right? Okay. And the only thing that really isn't defined as for now is this 3-form H. So in this setting, the 3-form is defined to be just dc omega. Okay. And using that expression over there, you can rewrite the second equation as this I dd bar of omega equals alpha prime times the difference of the traces. So these are the same equations as before. I've just replaced 2.2 with 2.4 like I said, and just to talk more in detail about them, the first one is just a Hermitian-Yang-Mills condition between the two metrics. The second equation is called the heterotic Bianchi identity. This is coming from some Green-Schwarz anomaly cancellation. This seems to be the more interesting equation to try and figure out. And the third equation is some condition on the torsion of omega. Okay? But work by Li and Yao shows that you can actually write it equivalently as this conformally balanced condition instead. So we'll make that replacement. Okay, so again, 2.1, 2.4, and I guess you can replace 2.3, 2.5. That is the whole system that we're trying to solve. Okay. One thing to note about this 3-form H, we can motivate it a bit geometrically because it appears as the torsion of a very special connection. So in the setting that we're considering, we're just looking at Hermitian metrics. We don't necessarily need it to be, it's just Hermitian, it's not necessarily Kähler, right? And so when you have a Hermitian metric, what's been shown is that there's a special connection that is Hermitian that also is specifically has the torsion being a skew symmetric. Right? So in this case, the torsion of that connection specifically is how we define H. So that this one is sort of motivate why H appears. And then just briefly, in the very simplified case, we have this heterotic Bianchi identity that has the traces of the curvatures. You can set this parameter to be 0, and that is a very simplified version of the system, and that just ends up being this pluriclose condition. So this is something that people also study, and the pluriclose condition is related to the study of closed torsion geometries, right? So yeah, when you have alpha prime equals 0, you're solving dH equals 0. If this system over here, right? That will be dH equals 0. H is the torsion of this special connection, so that is closed torsion geometry. Okay, so in order to solve these systems, we hopefully want to have examples of solutions to them, and the most special example of solutions to the system comes from Ricci-flat Kähler metrics. So this is supposed to be a generalization of Ricci-flat Kähler. Right? We saw earlier that Candelas, Horowitz, Strominger, and Witten solved the flux-free case, H equals 0, that gave Ricci-flat Kähler Calabi-Yau. So when you turn on H, it should generalize that in some sense. Okay. So very briefly, we can see that if you have a Kähler metric on a manifold, then by our definition of Calabi-Yau, it has vanishing first turn class. And in that case, you can run Yau's theorem to get a special Ricci-flat Kähler metric in the Kähler class. And after doing some computations, you can check that this Ricci-flat condition implies that the norm of upsilon with respect to the Calabi-Yau metric is constant. So when you have a Ricci-flat Kähler metric, you can pick the gauge bundle to be the holomorphic tangent bundle, and you can set both metrics to be the Calabi-Yau metric and solve the system. Right? The first condition is solved because it's Ricci-flat Kähler. The second equation is solved because the right-hand side, both curvatures are the same, so the right-hand side vanishes in that one. And if you're Kähler, then it's closed, so definitely completely closed. And then for the Calabi-Yau metric, the norm is constant, so omega will be closed in that case, so it's satisfied. So this is, in some sense, a generalization of Ricci-flat Kähler. You want to consider this system. Okay, so Ricci-flat Kähler is the a very special set of solutions. Of course, we want maybe non-Kähler solutions to this system, and so people have studied this, and I have a non-comprehensive list of what we know so far. So, for example, Hsuan-Yi have constructed non-Kähler solutions to this system over T2 bundles, on T2 bundles over K3 surfaces, and one can further generalize this. So with their ansatz, you have this Fu-Yau equation that you can generalize to the other dimensions, and you can study this modified Strominger system. This is also what has been done since. Other solutions have been found to the Hall-Strominger system through perturbing Calabi-Yau threefolds, done by Andreas and Garcia Fernandez. And then They and Yau have done this on complex Lie groups with specific types of Lie algebras. Otal, Ugarte, and Villacanza have solved this on nil manifolds and solved manifolds. Fei Huang and Picard have constructed infinitely many solutions. These have different topological types, but the model they have is vibrations over Riemann surfaces. And then Fino, Grancher, and Gazzoni can extend the work of Hsuan-Yi to a more singular case. So instead of T2 bundles over K3 surfaces, you have T2 orbifold bundles over K3 orbifolds. So this is sort of a list of what we know so far. But in general, you can see that these have largely been done in some highly symmetric cases or some dimensionally diffuse ones. Right? Yeah.
But your bundle in the equation, the capital E is a vector bundle, right?
Yeah.
Now it's T2 bonded.
No, this is the base manifold. So the base
Oh.
manifold is 6-dimensional.
I see. I see.
Yeah, so this is the,
Yeah, makes sense.
yeah. So for most of them, there's a, yeah, they have to take a bundle over the base manifold and then solve the system. But this is just the model of the base that they're looking at. Yeah. So done on some dimensionally reduced cases are highly symmetric. That simplifies the equations slightly. We can choose an ansatz and try and solve these systems. Okay, so now we start introducing the second part of the title of the talk, which is geometric flows. So we have this system of equations that we want to solve. Another approach to trying to solve the system is using a geometric flow. Okay, so Fong, Picard, and Zhang, they've introduced a couple flow of 2-2 forms and Hermitian metrics in an attempt to solve the system. So again, you can look at the system, this coupled flow. Equation 2.6 basically tells you to take this conformally balanced condition and flow it by your failure to satisfy the heterotic Bianchi identity. Right? And remember, our conditions were that this form needs to be closed, this right-hand side needs to be 0, and then we have a Hermitian-Mills condition. So by coupling in this downward heat flow, fixed points should naturally satisfy all these three conditions if you start with something conformally balanced. If you want to forget everything on the bundle, you can define a version of this flow just for the metric on the base by simply forgetting that your gauge bundle E exists. And you just forget all the information on there. So equation 2.7 doesn't make sense because small h is on the bundle, and then the trace of f wash f also takes place with things related to the bundle, so you also kind of forget that, and you can replace it with some arbitrary 2-2 form. 2-2 form that involves that. So this is this solves the whole system that we want, but you can solve a version of it on the base if you forget.
But for the solution, 2.8 on the solution split, it reduced when you retry the solution of the two solutions, 2.6 and 2.7, by solving 2.8.
I guess it depends on what you choose phi to be, because if you solve this, and then you pick a connection that solves this, then there's still this issue with what phi is. So, but
the two systems are not equivalent.
they're not equivalent. They're not equivalent. But I think in an attempt to try and understand this, it makes sense to try and understand
more general.
Just understand this first of all. Slightly easier. You don't have to take care of anything on the bundle. There's a flow of metric. Okay, so this is the coupled flow. There are things that we know about this flow. So what they've managed to show is that this flow actually induces a flow of 1-1 points. So 2.6 is taking this conformally balanced condition, which is the flow of 2-2 forms, and the first thing they show is that when you flow this, you can actually recover what the Hermitian metric should be. Right? So you need to somehow be able to extract what omega should be from 2.6, and you can do that. And then other things that you can show is that you preserve conformally balanced, which is good because that's one of the conditions that we like. If you start with something conformally balanced, then because the right-hand side of 2.6 is exact, you stay within the thing homology class as you evolve. And then stationary points of solutions of the Strominger system, you can also kind of see this by how the equations are set up. And then lastly, this flow has short time existence and uniqueness. So you can run the flow for some short amount of time and get some solution to it. Briefly, to extract the 1-1 form from these 2-2 forms, you can use a square root operation that's described by Michelson. In general, this is a n-1, n-root equation. It's just that we're on complex 3 dimensions, so n is 3, so you can take the square root. And then to show short-term existence and uniqueness, they just use a weak parabolicity of Nash-Moser implicit function theorem. Okay. So with these properties that we know, we have short-term existence. One natural question is to ask, what about long-term existence? When you run the flow, what happens as this goes on? And if we have long-term existence results for these flows under certain conditions. So again, probably not a comprehensive list in case I missed any, but they studied the simplified case when alpha prime equals 0. That's a nicer flow. It sort of just flows this, right? So this is DH is just right. So this takes at least the metric has to satisfy this condition on the flow. Turns out that this is nice because the fixed points are Fourier closed as well. And it turns out that in this simplified case, solving conformably balanced and Fourier closed actually implies Ricci flat scalar. So this is the alpha prime equals 0 version of this flow is take something that is just Hermitian and then gives you a Ricci flat scalar metric in the end if you can run it all the way. Okay. Other times where we have seen long-term existence type results are on P2 fibrations over K3 surfaces, on unimodular V groups, on fibrations over Riemann surfaces, and then two results like Kuhia-Ugarte on V groups again. And just as a reminder, there's other ways to sort of cast the system with different connections. So for these last two results, they use not the Chern connection. Okay. And again, we can see that most of these come from symmetric spaces or dimensionally reduced cases. Right? They're pretty much exactly the same list of settings that I said before. So our understanding for the system is quite decent if you look at specific models and come up with specific outcomes. Okay. And so, questions again, can we say something in general? And in the most general case, you can actually have this sort of long-term existence result, but mostly tells you some conditions that tell you when you can actually extend the flow to slightly larger time intervals. Okay. So what you can show is that under conditions on the dilaton, that is bounded both below and above, and making sure that torsion, curvature, and first derivatives, covariant derivatives of torsion are uniformly bounded along the flow, then if you just look at the flow in the metric and ignore everything on the bundle again, just for simplicity, then you can extend the flow as long as alpha is smaller than that condition. Okay. Slightly better way to interpret this is that when you solve the system, ideally you fix your parameter alpha first. So what this says from that perspective is, as long as the norm of curvature and the norm of torsion doesn't blow up too quickly, or doesn't blow up, then you can extend the flow to a slightly larger time interval. So sort of similar to other flow results, right, that you see. You don't want curvature or torsion to blow up. That will certainly cause some sort of issue with it. Okay, so I'll go through a quick sketch of the proof because there are some things that I'd like to highlight about it. Yeah. Okay, so for a result like this, there's this generic sort of steps that you would ideally like to follow, right? And this is what happened with the toy model case when alpha prime equals 0. This is not specific to this alpha prime equals 0 case, but you generally want to write something like this for most flows that you encounter, right? So these steps are generally universal. The first one is to actually have an evolution equation for the metric. That one might be more specialized for this flow because it's written in terms of this conformably balanced condition, but once you extract the metric, you can do everything else. Then you want to compute sheet type estimates. Then you can use the maximum principle to get higher regularity and bootstrap. And then you can, once you have that all the derivatives are bounded for curvature and torsion, you can use a standard argument to extend the flow. So the main things I want to highlight is when you try this naive method, some things will go wrong, and there are ways to fix it, which can work for similar flows as well. Okay, so when you start out, there's some assumptions that you need to have by assuming some base amount of regularity. So these assumptions over here are just assume that you have control of derivatives up to some level k minus 1. And you can make other assumptions. Because we're only considering the flow on the base, this phi is technically free to be something. We'll assume that that's as regular as you need it to be. And importantly, the assumptions that you have tell you that the volume of the manifold will be uniformly bounded along the flow, and that the metrics are going to be uniformly equivalent along the flow. That's one thing that will be shown. Okay, and so the first step is to rewrite the flow equations. This has already been done. You can see the schematic models for how the metric flows, how the curvature flows, and how the torsion flows. There are some terms that are being obscured away, H1, H2, K1, and K2. These are generically going to be good terms. You can characterize them by the number of derivatives that they have with respect to these structures, and they are okay. They really cause no problems. So once you have these, you can use these to get evolution equations for derivatives of curvature and derivatives of torsion. That's what ultimately we want. But from this schematic equations, you can see that there are probably going to be some issues, right? When alpha prime equals 0, everything is fine. It looks like it flows by a heat equation plus lower order corrections up to some conformal factor. But if you look at equation 2.13, we see that with the red terms there, we have problems, right? This nabla bar of Rm star Rm is on the same level as the Laplacian, right? So that will start causing some issues. It's also not a Laplacian, which is why it's written in this form. But
in 2.12, equation 2.12, the left-hand side is the derivative of metric, right?
Yeah.
The right-hand side is Riemann curvature tensor. Is it Ricci or Riemann?
It will be Ricci, but this is just schematic, right? So this is something involving the curvature tensor. This is something involving the torsion tensor, contracted with the complex conjugate of the torsion tensor. Right. So there's a bunch of terms missing that are being obscured, but for the Xi estimates, we really just care about what these terms look like generally. Yeah, but you can see beforehand that there's probably going to be some issues, and that basically comes up. So when you start mimicking everything, you can get some point-wise estimates, which you would like to do because you would want to run the maximum principle. But when you take your test function and you run through everything, you start seeing some issues. But what you can do is you can naively follow what happens when alpha prime equals 0. And when alpha prime equals 0, this point-wise estimate is actually nice. Right? If you ignore all the colored terms, you have your test function evolved by something that is bounded above by a Laplacian, a negative term, constant, the term itself, and a generic good term. Right? So when alpha prime equals 0, this is a nice thing to do because you can use the maximum principle. It's in a nice form. But when alpha prime is not equal to 0, then these extra terms start causing some issues. Okay? The one thing that hasn't been defined here is this alpha naught. This is just a dimensional constant. We can mostly ignore that. Okay. So like I said, the red terms are higher order, but they're not Laplacian, so you can't use the maximum principle to deal with them. You'll have to use a different method. But the good news is that these terms over here in red, they look like divergences. Okay. You can mess with them so that they end up actually being divergences. So if you want to get rid of them, what you can integrate and get something nicer. This is exactly what it is. So instead of computing the point-wise Xi estimates, you can integrate everything and get integral Xi estimates instead. So this is the same equation, just with integrals everywhere and p's everywhere. But after some integration by parts, you can make this actually divergence, and then you can divergence theorem nonetheless. And after doing that, this looks a lot nicer. You have that the evolution of this LP norm of the test function is bounded by a uniform constant because the volume is uniformly bounded, and then times the function itself, and then these blue terms. The blue terms are still annoying, but at least in this coefficient there's a negative sign here. So if you pick a condition on alpha that makes this the dominant thing, you can get rid of the blue terms. So this is the condition on alpha prime that you get. As long as alpha prime is less than that number, then we're using Young's inequality, so epsilon is free to be picked. This can be a dominant term. You can make this a small as you want, and then you can make the fluid times negative and ignore them. And so you're left with this inequality. So this is, beforehand was where we would like to use the maximum principle. Now we're left with something like this. And so instead of the maximum principle, we can use Grommel's inequality, which is exactly what the setting is. So Grommel's inequality says that if you have two functions, and then the derivative of one is bounded by the product of both of them, then you can estimate u by its initial value. So exponential and integral. Ultimately, it really just matters that our setting is exactly this. You can pick u and beta appropriately, and then you can estimate this LP norm over time based on its initial value. So this is what we're using to control everything over time. And based on the choice of the test functions, which are derivatives of curvature and derivatives of torsion, then you have that these are bounded along the flow, and so you have L2P bounds constructed from this whole argument. Now, there's still some issue. We started with point-wise bounds, but we've got L2P bounds, so we have to get back to point-wise bounds. You can appeal to an argument of Hamilton and use the Sobolev embedding theorem to go back from LP bounds to the point-wise bounds. Ultimately, it's just under the same assumptions of regularity, you need to be able to bound sort of one order higher, and then you can kick in the Sobolev embedding theorem. And basically everything works the same way. You can, under the same assumptions, get pretty similar expressions, and you get a similar condition to alpha prime. And this is what allows it to work. So, yeah, you just take your test function and go one order higher. You can run pretty much exactly the same argument. So once you do this, you can use the Sobolev embedding theorem, and you can get point-wise bounds for the norms again. And the important thing here is that this bound on alpha prime is exactly the same one we saw before, and it doesn't depend on k, where k is the level of regularity that we're assuming so far.
You Sobolev embedding because you already assume the metric is equivalent to
Yeah.
the initial metric.
So because the metrics are uniformly equivalent on the flow, the Sobolev constant doesn't do anything funny.
I see.
Yeah. So again, the condition alpha prime doesn't depend on k, so you can bootstrap all the way. So after this, you can really start with some amount of regularity and go all the way up. There's some additional complications when k is small, but ultimately they go away. Just the main issues is that for the product rule, and you're trying to write everything in terms of quadratics of unknowns, when the number is small, and when you use product rule, you get more unknowns. So something like this will be, for example, cubic and unknown, right? When k equals 2, we don't know anything about d2, d3, and d4, but then our terms involve something cubic. This causes some issues, but the main way to do it is to just use a different test function. Ultimately, everything works out fine. The test functions here are not very important, but just pointing out that there is some slight unguents to the argument that needs to be done. So everything works fine. You get a much tighter bound on alpha prime. And then you can extend the flow. This one is just a standard argument. Okay. So at this point, I'm sort of done with the six-dimensional version of the flow. This is sort of as far as we've gone with the anomaly flow so far, and trying to solve this system. So we have some natural questions, right? What next steps can we do? Well, like I mentioned, I ignored everything on the bundle, so at least the flow has some decent properties when you forget what happens with the connection. The next step that maybe one would like to do is try to see if you can have a similar result when you actually couple in the connection, right? This is the full flow, couple flow that you'd like to solve, and see what sort of issues would stop you from running the flow when in the basement, when everything's moving together. Great. Yeah. Okay. Obviously, there are going to be challenges, even though we demonstrated that we can kind of understand this flow on the base okay. Right? We have some results there, and then this is just a Donaldson heat flow. When you couple them together, a lot of estimates get mixed up with each other, and you have to yeah, you have to re-update everything, right? The C0 estimates for Johnson Equal, for example, they get messed up because the base metric is moving. So all these things have to be re-obtained. Of course, there are other questions that you can ask about this, but this is one that I naturally see. Okay, so that's the 6-dimensional case, and at least how far geometric flows can go with that. Now I move on to the 7-dimensional case, and this will involve G2 structures. Okay. I don't assume that everyone knows much about G2 structures, so I'll have a very quick recap on what we need exactly for a G2 structure. Okay, so like SUN, right? SUN gives us our SU3 structures, the coffeehouse stuff. The group G2 is one of the possible holonomial groups in Berger's list, right? And so it's one of these exceptional holonomies. Importantly, what we mostly need is that a G2 structure is just a special 3-form on a 7-manifold. So, if you have a 3-form that determines a metric tensor via this expression over here. This is a very nonlinear expression in this 3-form phi. Yeah. So the class of 3-forms that satisfy this are something called positive or definite 3-forms, and this is an open set in the space of 3-forms on 7 manifolds. Assuming that your manifold is orientable and spin. That's the only 2 topological conditions that you need for such a form to exist. Okay. So if this 3-form determines a metric and a volume form, then you can get all the associated structures. You get a Hodge operator, you get this dual 4-form, and you also get a cross product. So 7 dimensions is another special thing where you get a cross product, and it comes exactly from this 3-form. One other way to view G2 structures is just a point-wise identification of your tangent space with the imaginary Arconians. So it's like how for Taylor you identify point-wise with Cn, and then your 2-form has this coordinate expression. You can do a similar thing for G2 structures, but the sample G2 structure on R7 comes from the imaginary Arconians. So all this cross product thing comes from multiplication of Arconians, and then that turns out to be exactly skewed.
Is this G2 the G2 in the classification of semantic for the algebra?
Sufficeable, sorry what?
The algebra.
I should be. Yeah. G2, the Lie algebra G2 is the 14-dimensional Lie algebra, right?
I mean, this is the Lie group.
Yeah, and this is the Lie group for that.
Okay.
Yeah. Okay, so G2 structure is really just a special 3-form. Other things that we'll need is that if you have a G2 structure, then you get an orthogonal decomposition of forms. So your 2-forms split into the 7-component and a 14-component, and your 3-forms split into a 1, 7, 27 component. Right? And just to be explicit, the 2 7 components really just come from vector fields. It's what happens when you take a vector and hook it into phi. Your 3 7s are also vector fields. It's what happens when you take a vector field and hook it into psi. Right? That's a dual size star of phi. And then 3 1-forms are really just multiples of phi. Okay, and you can get decompositions for 4 and 5 forms using the Hodge star. So this decomposition of 2 forms, being 2 plus 2 7 plus 2 14, is something that we can use, right? So also just note 2 14 is, since the Lie algebra thing will come up, this is the 2 14 forms are isomorphic to that space. Okay. So since we can decompose 2 forms, you have a slightly more fine decomposition of the space of 2 tensors, and you can actually associate 2 tensors to 3 forms using this contraction operator. And it turns out that when you run this contraction operator on the 2 tensor, the kernel is exactly the 214 forms, and then you get isomorphisms between these 3 bases. So the 3 form is really given by a function, a 2-7 form, which is really a vector, and then a traceless symmetric 2 tensor. See, there's this identification between these 3 spaces. So when you want to understand 3 forms, you can really just pick out these components. Okay. The next thing that we'll need is torsion, this idea of torsion. And for a G2 structure, the torsion is measuring the failure of phi to be parallel with respect to the symmetry of the connection. So again, for a G2 structure, phi is given by so your 3-form phi determines a Riemannian metric, and that will in turn have a Levi-Giguère connection. This is a highly nonlinear way to define a metric, so that equation is not linear, trying to solve nabla of phi equals 0, but it does actually define this 2 tensor. And another way to look at torsion is using this result Fernandez and Gray, and this tells you that your torsion can really be thought of as d phi, the failure of phi to be closed and co-closed. Okay. So we have 4 torsion forms using a decomposition. d phi is a 4 form, so we have a decomposition there. d psi is a 4 form, and you get these things. It turns out that these two are exactly the same form. So you get these 4 torsion forms, and via this isomorphism between forms isomorphisms between these forms, you can actually rebuild this 2 tensor from these 2 expressions. So you can think of torsion using this equation and you get this 2 tensor here, or you can think of torsion using these 2 equations and you get these 4 forms over here, and these relate because each of these forms can get you a 2 tensor. And then there's 16 torsion classes, depending on whether these are 0 or non-zero, and a few ones that will show up later are the special ones, or some special ones. So we have torsion-free G2 structures when everything is closed and parallel. You have closed G2 structures when phi is closed. You have co-closed G2 structures when psi is closed. You have nearly parallel G2 structures when d phi is just a multiple of psi, and then you have these weird ones called integral G2 structures when tau 2 is 0. These are much nicer to deal with, as you can see, because the conditions are just very differential, right? But integral G2 structures are actually the ones that will be important for what comes later, and they're harder to understand. Right? Firstly, tau 2 equals 0 doesn't really come out from some differential condition. It's hard to isolate exactly that component. The other thing why they're important. The reason why they end up being important for us is that these are supposedly an analog of having an integral complex structure. Okay? Even though we're working in 7 dimensions, there is no actual complex structure. These are supposed to be some analog of that. There's a notion of a Dolbeault cohomology for G2 structures that exists when tau 2 is equal to 0. Although I'm not fully I don't fully understand this connection to integral complex structures, but there is some notion of this. Okay, so that was a very quick recap. I'll try and mention things again as they come up. But the idea here is that we still want to solve this this model that I brought up at the start, right? So you can recast Strominger's condition in the G2 setting. So the equations are very similar. So in G2, in the G2 setting, what do you want? You still want a vector bundle, and you want metrics on the base, and you want you want connections on the bundle instead. Again, not instead, right? So for the G2 case, you still want a vector bundle, and what you want is a connection on the base and a connection on the bundle that satisfy these equations. And these are similar to what we see before, right? This equation is the analog of Hermitian-Yang-Mills. This is, again, looks like the heterotic Bianchi identity from before. Looks pretty much the same. And then before we had a conformally balanced condition. Now we have a conformally co-closed condition. But the dialecton here is less obvious. Okay. And in the SU3 case, there's some freedoms to how you choose these connections. Here, there's also some freedom on how you choose this connection and how it should be related to phi. This equation sort of doesn't see the choice of connection as long as it's chosen appropriately. The last thing to define here is the free form H. So in the SU3 case, this form H was dc of omega when you had your Hermitian structure. Now this is some weird combination of torsion showing up here. Okay, so these equations are sort of the analogs of what we had before. This is the G2 instance Suan equation, which is like Hermitian-Yang-Mills, like I said. This is heterotic Bianchi identity. And then the last equation is conformally co-closed, but it actually does tell you something about the torsion class of G2 structures that we're working with. So if you expand this out, and you can, that equation will imply this, and you can extract out torsion extract out some conditions of the torsion. In particular, it tells you that tau 1 is exact and tau 2 is 0. So we're lying in this integrable class of G2 structures.
But the connection in equation 3.2 is not the G5 connection. It's not the G5, not the G5.
It can be, it doesn't have to be.
It doesn't have to be.
Yeah. I'm also being a bit loose on exactly the definition. So,
because in the in the previous case, you choose it to be the
I choose it to be the Turing connection. Yeah. There's some freedom to choose. So before I chose the connection to be a Turing connection, but I said there was freedom to choose any connection as long as it's unitary. Here, I'm not setting a specific connection because I'm going to only look at alpha prime equals 0 and forget a lot of information. But in general, there's a choice on how to choose the connection. There's freedom to choose the connection in some way.
Then it doesn't use essentially the G2 structures, the G2 equation.
Yeah.
To induce a metric image.
Yeah, there's one equation that I forgot to write down. It also requires that the connection of this also has to be a G2 instanton. So there's this one additional equation I forgot to write down. So F needs to satisfy this equation, R also needs to satisfy this equation.
I see.
And that will be an additional condition.
But it still didn't use essentially the defining equation of G2 where you induce a metric G5, but they didn't use that metric.
Yeah, you don't have to use it. Although I think depending on which source you read, some will say specifically you should use the Levi-Shapiro connection. Some will say that you need to use there's a special connection that I'll point out in the next slide. So there are natural connections that come from phi, and some sources say that you should prescribe exactly this metric, this connection from phi. I'm going to forget a lot of the things about connections because the easiest case is when alpha prime equals 0 and then it doesn't see any of that information. Okay, so we had this free form H that looks a bit more weird in the setting, and just to, again, geometrically motivate it, it's again the connection, the torsion of a very special connection. So for G2, before we had the Hermitian case and we had a special connection with skew torsion. For G2, you have exactly the same thing. When you have a G2 structure, there's a special connection with skew torsion, and the torsion is exactly this H form over here. So if it's unclear why H shows up as this form, this is sort of why. It just happens to be the torsion of this special connection with skew torsion. This also only happens for a G2 structure when it's integrable. If it's not integrable, you don't have this. You can define this form, but it's not the torsion of the connection. And then in the simplified case, we're really solving this dH equals 0 equation, and these are called strong G2 structures in torsion. Okay. So just like how Ricci flat Kähler structures are special solutions to the SU3 case, torsion-free G2 structures are special solutions to this. So if you have a torsion-free G2 structure, then you have natural choices for what you want. If it's torsion-free, then this Levici-Vida connection, you can show that it's a G2 instanton, so you satisfy 3.1. And then if it's torsion-free, H was defined using the torsion of phi. So if G has no torsion, if phi has no torsion, then H is 0, and d psi is also 0. So when you have a torsion-free G2 structure, you can have natural things that very easily satisfy this. Of course, we don't necessarily just want torsion-free G2 structures. And so people have constructed more solutions. And again, a non-exhaustive list, but these have been done on either dimensionally reduced cases again or on symmetric settings as usual, right? So, yeah. And then I threw in some approximate solutions as as well. But again, these all rely on some sort of reduction or symmetry somewhere. Okay. Now is more speculative things, right? We had this anomaly flow for SU3 for 6 dimensions. Now the question is whether or not you can extend all these ideas into 7 dimensions. We've already seen that some of the analogy holds. You can recast the Strominger system equations in 7 dimensions, but now the question is whether this geometric flow approach still works. Right, so we want to know whether there's a G2 analog of the anomaly flow. Before we continue, there are going to be some issues with this. Firstly, we're in 7 dimensions, so there isn't really a complex structure, right? When you're working in the SU3 case, you have omega, you have epsilon, and you can sort of tune both of them separately. Here in the G2 setting, you only have one form. You have one form phi, and this determines everything. Okay? So in a sense, G2 structures are more rigid. Right? You can't decouple it. Phi determines everything. It determines the metric. It determines the cross product. So this is some potential issue that will show up that could cause an issue, but either way, we can still try and continue. Ashmore, Minassian, and Proto, they've proposed and derived a framework for how anomaly flow should look like essentially. And this is the lead that we'll try and follow. Okay. So we'll do the very simplified case and ignore anything with alpha prime in it. So assume alpha prime is 0. Right? If you want anomaly flow to work, it should work in all the cases. Let's take the simplest case. So when alpha prime equals 0, these are the only 2 equations we want to solve. And here we're just looking at the base. Okay. And so if you want to mirror what happens in the 6-dimensional case, your flow should look something like flow this equation by this equation. Right? They're both 4 forms, and you can rewrite this equation like that. You're flowing conformally co-closed by minus dH. And this is analogous to what we had before, where you flow conformally balanced by dH. Okay. One thing here is that in the SU3 case, you have this dilaton that's given by this norm. You don't have this separate complex structure for G2, so you have to find a way to determine your dilaton F naturally. And so what we've done for this is, instead of looking at this as the norm of epsilon, you can actually think of this as the ratio of volume forms. So you should probably think of F as a ratio of volume forms in some way. So we've picked the reference volume form and done all of this. Okay. So one good thing about defining the flow like this is that if you can construct G2 structures out of SU3 structures by crossing in a circle, right? Or taking a principal S1 bundle. So in some sense, if you want all these flows to work nicely with each other, the G2 version of the flow should reduce down to the SU3 version of the flow under suitable undoubted models. So it turns out that you can do exactly this. If you have a compact Calabi-Yau threefold with this conformally balanced structure, you can construct the G2 structure on the circle bundle. You can ignore the coefficients over here; those are just there to make the sum calculation simple. But a conformally balanced permission structure on a Calabi-Yau threefold allows you to construct a conformally co-closed G2 structure on the circle bundle. And it turns out that when you use this ansatz and run the flows with each other, they actually reduce nicely. So again, on a compact Calabi-Yau threefold with conformally balanced metric, you can construct something on the circle bundle that's conformally co-closed, and so you can run the anomaly flow on the base, and it induces exactly the anomaly flow on the circle bundle, or you can run the anomaly flow on the circle bundle and it'll induce the anomaly flow on the base, which is a nice property to have with this ansatz. Of course, here you have to pick some reference volume form, and you can do that with respect to all the structures on the base. Okay. So one thing about this anomaly flow is that you can rewrite H in terms of in a different way. So it turns out that H looks, well, dH looks almost like a Laplacian. Right? So the flow that we defined was flow conformally balanced, conformally co-closed by minus dH, and this looks like some sort of conformal version of a Hodge Laplacian, right? d star. I ignored the d star d part because you assume that this is already closed, so d star d is 0. d star d of e to the minus 2f psi is 0. So this looks like a conformally co-closed version of another flow that's been studied. So this is Laplacian co-flow that takes the four form and flows it by its Laplacian, and then throws up some additional terms as well. So this is, these two flows kind of look similar, so you can think of it as a conformal version. You can think of this as a conformal version of that. But for this flow, there's been some modification terms added on with this parameter c that adds on more of this d of tau naught phi term. So instead of just studying this flow, we will also modify it and have additional terms that you can throw on the flow. Okay, so we're studying this other class of flows, and with respect to what I said earlier, if you have this flow that sort of goes back and forth between 6 and 7 dimensions, now I'm adding on extra terms. Does this affect the same thing? Does it affect any of that argument? It still doesn't, because the ansatz that we chose before doesn't actually see the terms that we're adding. So this new class of flows that we're saying to look at actually still does the same dimensional reduction as before. So running this flow on the circle bundle is still fine. It still induces the flow below, and then vice versa. Okay, so now that we have this class of flows, we want to do the normal things. We want to look at their fixed points. We want to look at all the properties. So for fixed points, you can actually solve everything. You can look at the fixed point equation, fixed point condition, and then use G2 decompositions to actually solve everything. Show that the fixed points are relatively nice depending on the value of c that you're adding. Importantly, the value that we ideally want for the original version of flow is c equals 4/3. You can see that c equals 4/3 does appear as a special value, which is somewhat to be expected. But you can see that if c is not 1, then you can really determine tau naught by f exactly, up to some constant. C is 4/3, then tau naught has to be constant, and then you have some special cases where c is 10/7 or greater, then phi has to be specifically nearly parallel or torsion free. Other things you can do is you can look at how the metric moves, right? The G2 structure induces a metric, and you can figure out how the underlying metric moves. In general, it's pretty nice. It flows by this conformal Ricci flow, plus a Hessian term, plus this additional thing, which is like a generalized Ricci flow. And then you have these lower order corrections. And again, c equals 4/3 comes out as a very nice case to have. Right? So in general, it's the conformal generalized Ricci flow plus Hessian plus the lower order terms. And when c equals 4/3, all the lower order terms go away, and you really just get this conformal generalized Ricci flow plus Hessian. So the c equals 4/3 case, fixed points of this are actually gradient generalized Ricci solitons. You can construct that as this. Okay, and then last things that you want to do are look at short-term existence and uniqueness, and this is where things start becoming issues. So the reason why we want to study this, propose this flow, is because you hopefully want to extend anomaly flow to 7 dimensions. You can get good properties for the flow that you want, with the exception of short-term existence and uniqueness. So this will end up being an issue. So we compared it to the Laplacian coflow because of how the evolution equation looks. And it turns out the Laplacian coflow, without the modification terms, is not so nice, because we don't know how short-time existence is unique. This is contrasted with another flow that's been studied, which is the Laplacian flow, which has short-time existence and uniqueness. But the reason why there were modification terms added to the Laplacian coflow was to fix issues in the principal symbol. So you need to throw on these terms, and you can fix issues, and you can get short-term existence and uniqueness as long as c is strictly less than 1. Since our flow looks like a conformal version of the modified Laplacian coflow, you can actually just use the same idea as a proof, and you can get short-term existence and uniqueness under the same conditions, as long as c is less than 1, which now becomes a problem because the nice value of c that we wanted was c equals 4/3. So it seems like you have to either pick to have nice fixed points and nice evolution of the equation, a nice evolution of the metric, or have short-term existence and uniqueness based on this analysis so far. Slightly unfortunate. Okay. So on the topic of still trying to use geometric flows to study this, there's been another flow that's been proposed by Garcia, Fernandez, Moreno, Payne, and Streets. It is very similar to what we've looked at. You can see that they're still flowing conformally co-closed by minus dh plus correction terms, exactly. The only difference for them is that they've defined their dilaton differently. They have no longer made it a quantity determined by phi, and they've augmented the lower order terms of the flow of the function. So they have all these additional parameters that you can tune, and for some choices of their parameters you can actually get short-term existence and everything, and the fixed points are torsion free. In terms of how it relates to the other flow that I was just mentioning, the values for k that they have that are nice basically correspond exactly to c less than 1 for short-term existence. So they're not gaining anything new in terms of this evolution equation by fixing the dilaton slightly differently. But they've managed to get a flow that gets you torsion-free G2 structures by just fixing, by augmenting lower order terms in their flow in the dilaton. And they get all the nice properties anyway. But in terms of solving the Strominger system, this flow doesn't exactly solve that, right? They just have a flow that goes to torsion-free G2 structures. Anyway, one thing to finally just to mention about maybe why these flows fail to solve this thing is the short-term existence issue. Everything that worked well needed this additional modification term somewhere. The coefficient is to be determined, but a general result by Drivedi, Ioannidis, and Karagiannis is that if you have a generic flow of G2 structures that you can write in terms of how things are evolving, so this term here is basically saying that your flow should look like a Ricci flow. Right? Everything in this bracket is determining how the metric moves, and everything in this bracket doesn't determine the metric, but it's some sort of vector component of the flow. But if you prescribe a flow that looks sort of like this with lower order corrections, then you only have short-term existence and uniqueness under certain conditions on the values of A, lambda, B1, and B2. There's some conditions where you can push this a bit further. So instead of B1 and B2 being greater than or equal to 1, you can really just think of B1 and B2 being greater than 0. But anyway, there's some conditions to get short-term existence and uniqueness of the flow. If you want to prescribe something that is what they call Ricci-like. Okay. So when you study the flows that we're proposing, or that was also proposed by Garcia Fernandez, Moreno, Payne, and Streets, you can modify this Laplacian flow, you can modify the Laplacian coflow and put the conformal factors. It turns out that you do get a Ricci-like flow. This A parameter is minus 1/3, which is fine. But in terms of this was B1 plus, we wanted B1 plus B2 greater than 0, but you're just left with a C1. So this is where all the C less than 1 conditions keep coming up, right? So it seems that if you want your flow to look like something involving a Laplacian, then the vector component without modification terms generally wants to move in the wrong direction. So this is something that needs to be overcome somehow. Okay. So just as some last remarks about this flow, the whole idea was trying to generalize and get an analog of the anomaly flow for G2. We'd ideally want these conditions, right? You would want your fixed points to work out, right, which is this dh equals 0, at least for the simplified case. You want the equations of motion to work out. You want to preserve conformal closure, and you want to refer this as uniqueness. It seems that G2 structures are somehow a bit rigid, and you need to sacrifice one of these properties somehow, right? The flow that I first proposed lacked short-term existence and uniqueness. The flow that was proposed after, they modified everything, so they get short-term existence and uniqueness. They preserve conformal closure, but they lose these two, right? So something needs to be done about that. But as for now, there are still ways to maybe salvage some of these ideas, right? If you look at this thing, this equation, if div t somehow is completely lower order, then you can artificially inflate this term. Great. And so one way to maybe make div t completely lower order is maybe to preserve tau naught equals tau naught being constant. And that's one way. Another way is maybe preserve tau 3 equals 0. But as of now, it's unclear whether you can actually preserve such of these conditions. But theoretically, it is possible that we are looking at two general of G2 structures. That starting with conformal closure is not enough. You need to start with conformal closure plus tau naught constant, or start with conformal closure and tau 3 equals 0 or something like that. So it is possible, but it's still unclear. Okay, anyway, yeah, there's natural questions. Can you show that tau naught constant is preserved by the flow? As of yet, I haven't been able to do something like that using a maximum principal argument. Still not clear. And then maybe even more ambitious is that if this somehow works, can you include the alpha prime correction? It's also possible that the alpha prime corrections make things better, but in general, I don't think that would ever be the case. Yeah. Anyway, that's
Any questions for the speaker? No, let me ask a question. So in your work with spiral and p-type, you there is a fixed dimension for S1, right? You consider T2.
Yeah, so that was sort of the motivating example.
Yeah, I was wondering if there's, in general, is there any principle between the solution of the whole Strominger system in 7 dimensions and the 6 dimension? Is there any relation? No. Is there any relation in general between the abnormal flow in 7 dimensions and 6 dimensions? So beyond that setting.
So for the flow, yeah, basically, if you define the flow this way, then solving the flow on the base will solve the flow upstairs and vice versa. So the solutions are exactly aligned with each other.
But it used the structure that it has to be a product of S1 and
yeah.
Yeah. In general, we don't have this correspondence.
In general, you can do something similar with principal S1 bundles if you want to I don't know how other ways you're going to construct a 7-dimensional manifold from a 6-dimensional one. If you want to keep compactness, you either cross in a circle or take a S1 bundle somehow. Right. And so in both of these cases, you can get something similar where you should be able to dimensionally reduce. Under a particular Tristan lockdown. Yeah.
And in this result, you also show you also know the fixed point, right? You also determine the long-term existence, the fixed point is known.
So for the fixed points of this particular setting, it's fine because you're running the anomaly flow with alpha prime equals 0 on base, and that's well understood.
I see. So under this setting, when alpha prime is non-zero, it's not known.
Yeah.
Even in this setting, alpha prime is
Yeah, we didn't do anything with alpha prime non-zero because that seems to be the harder thing to do, right? If you want to generalize the flow, you should do the easiest case first, and then throw on the additional stuff afterwards. So it's more of trying to see what happens if you want to solve the equation, right? Yeah. And the easiest case is when alpha prime is 0. So yeah.
Thank you. Any further questions or comments? Or if no, then let's thank the speaker again.